So this is 4.5, uniform circular motion. Okay, so in uniform circular motion, we can think of a particle moving along a circular path with a constant speed. And so even though the particle's velocity will be changing, as we will see shortly, since because the direction is changing, if the magnitude is the same, we will say the speed is constant. So let's consider the circular path shown below. So I'll draw a circular path like that. And in this circular path, we have velocity v. Let's put another one here, v and v. So what I'm showing here is that v has a constant magnitude because the arrows are the same length, but the direction changes. Okay, so the direction of the velocity vector is changing for a particle in uniform circular motion. So I'll put the radius here, r, for this particle in the circular path as shown there. Okay, so if we think of the particle as moving through one complete revolution, then we can determine, or we can at least get a formula for the speed of the particle in the circular path. So I'll do that in the next frame. We can say that suppose the particle goes through one revolution, we can define speed v. So we shall say the speed v is equal to the distance covered in one revolution divided by the time taken. And since the particle is going through one revolution, we shall say the time is the time period. So the distance covered will be equal to the circumference of the circle, and the time it takes will be equal to the period t. Let's use uppercase t. And so the speed v in the circular path, let me rewrite this, hold on. So the speed v is just equal to the circumference, which is 2 pi r, divided by the time period t. Questions at this point? So this gives us a starting point, at least to study uniform circular motion. And just like we did with linear motion, in order to study uniform circular motion, we can put the motion on a coordinate in a coordinate frame. So we can start off with our xy coordinate frame, because uniform circular motion is just motion along or in a flat plane. So it's a lot like what we've been looking at. It's a lot like projectile motion, but it's a little bit different. It's in a plane. So we can think of using our xy plane, but we shall instead define the angular position of the particle, as we will do just in the next frame. So let's look next at angular position. And let's call that angular position theta. So we shall say that uniform circular motion or circular motion is motion in a plane. So let me just get that down. And this, of course, applies to non-uniform circular motion. So we'll say uniform circular motion is motion in a plane. And we can study circular motion by first let's specify the angular position. So we specify angular position theta in the xy plane. So suppose we have x here and y here, and we can think of a certain point here to be the angular position. So it means the particle is at a position, it's at an angle theta, and then at a distance r from the origin. So r is the distance from center of path. You will know this as the radius, and theta is angular displacement from the axis, or it's an angle from the x-axis. So we shall say angle from x-axis. So any questions at this point? Okay, so what we've shown here is the angular position of a particle moving along a certain circular path. One of the things we can look for on this is looking at the arc length. Let's say S is the arc length. This is the length of the arc of the circle. So our arc length will be shown below. So this is X again, and that's Y. And we can think of this length here as S, the arc length. This angle is theta, and this is R. So with our arc length S, this would be equal to R times theta. And this is the angular position theta. R is the distance from the center, and S is your arc length. So angle theta, theta is in radians, S in meters, and R is also in meters. So we can say theta is equal to S over R, and then we can say that for one full revolution, S, the arc length, is equal to 2 pi R. Therefore, the angle theta will be equal to the arc length, which is 2 pi R divided by R. Cancel out your R, so theta is equal to 2 pi for one revolution. So the angle theta is equal to 2 pi. Of course, this is also for a full circle. So when it goes through one circle, we can say that's one revolution. So we can say one full circle is one revolution. So let's go on with that. And that's equal to 360 degrees, of course. So we can have some units. So we can say one revolution is equal to 2 pi in radians. And then we can say that 2 pi radians is equal to 360 degrees. And of course, we can also say that one revolution is equal to 360 degrees. So this gives us a way to just convert between degrees, radians, and revolutions. So our angular position is in radians, and so the radian basically is not a true unit, so we'll just say radian. It doesn't have, we will not use a letter to represent radian. So suppose the particle goes from one angular position, let's say theta 1, to a different angular position, theta 2. We can look at the angular velocity of the particle next, at least by specifying the angular displacement. So we'll be able to get angular displacement, and then from that get angular velocity. So let's look next at angular displacement. Let's say that suppose the particle goes from position 1 to 2. So let's call it angular position 1 to 2. Actually, let's just go from angular position theta 1 to angular position theta 2. Let's not talk about the time yet, so we'll talk about that later. So it goes from angular position theta 1 to angular position theta 2. Let me draw it down here. So this is again x, and that's y. And we can think of position 1, position 2, and so this is theta 1, and this whole thing is theta 2. And so this space here is delta theta, where delta theta is equal to theta 2 minus theta 1. And this is our angular displacement. So theta 2 minus theta 1 is angular displacement. So the object goes from one angular position to the other. And if you like, we can say this is S. The arc length is again S. Actually, let me use delta S for the arc length. So we can say that delta S is equal to R delta theta. We can put that aside. So the angular displacement delta theta is given by angular displacement is delta theta, and so delta S is the change in the arc length. All right, so let's now look at how let's look next at angular velocity. So we've defined angular displacement, so we can now define angular velocity. So we can say with our knowledge of angular displacement, we can now find angular velocity. And let's say angular velocity is omega. So let's put the angular velocity, omega. So angular velocity, of course, is a vector quantity. It is the angular displacement with respect to time. So we can define it first of all. So we can define that by time interval delta t. So average angular velocity is equal to angular displacement divided by time interval. And a lot of what we are doing is following the same line as what we did for linear velocity. We first found the displacement, and so from there we could find the linear velocity as a displacement with respect to time. So we are doing the same thing here. Our angular velocity is just the angular displacement with respect to time. So the letter omega is used to represent angular velocity, and it's equal to the angular displacement delta theta over the time delta t. So this is average angular velocity. Let's put AVG there for average angular velocity. And we'll say that, note that this is a vector, and the unit for angular velocity is going to be radians per second. Okay, so the unit is radians per second. So having found our angular velocity, or average angular velocity, we can look next at instantaneous angular velocity. So I'll put that on the next frame. Okay, so instantaneous angular velocity. So instantaneous angular velocity, of course, is average angular velocity in a very short interval of time. So just like we did for linear angular velocity, we shrank the average just as we did for the linear angular velocity. When we wanted to find instantaneous velocity, we just shrank the time interval to a very tiny point, and that gave us our instantaneous velocity. So we can do the same here for instantaneous angular velocity. So we can say that with omega average equal to delta theta over delta t, we can find omega instantaneous, and we can just write that as omega, and that will be equal to the limit of delta t approaching 0, delta theta over delta t, which then becomes d theta dt. Okay, so the instantaneous angular velocity is just d theta dt. So we can say that graphically, the angular velocity is just a slope. So this is the slope of the theta versus time graph. Okay, so just like we had for linear motion, velocity is a slope of the position time graph. In the same way, angular velocity is the slope of the angular position versus time graph. So we see that omega is equal to delta theta over delta t, and we can say that delta theta is equal to theta final minus theta initial. So we can say that omega is equal to theta final minus theta initial over delta t. So this allows us to write theta final equals theta initial plus omega delta t. Any questions at this point? Let me save this and then we'll go from there.